All right, class. Welcome back. Today we're going to look at kind of the last topic for geometry this year. I saved it for last because we really needed a lot of skills leading up to this. We've looked at circles in different ways, but today's the time that we actually are going to figure out how you write the equation of a circle that you can graph on the coordinate plane. To get us started, I actually created a circle on the coordinate plane and centered it at the point 0, 0. So it's centered right at the origin. The radius is 4 units. So those will be all 4-unit measures. And we're going to talk about how we create this circle with a radius of 4 units centered at the origin. It really all comes down to the Pythagorean theorem, and that's something that we've worked with last year, this year. You should be really comfortable with it, so hopefully it makes this equation make a lot of sense for you. If you think about a circle, by definition, it's the set of all the points that are equidistant to that center point. So every point out here on the circle ends up being the same distance from the center. We've talked about how to find the distance on the coordinate plane, and this came when I was kind of hesitant to talk about what the distance formula was, but use the Pythagorean theorem instead. And that's really helpful now, because to find the distance of these points, I can draw a right triangle. So if I go over along the x-axis and then up in the y direction and I connect it, that right triangle will give me the distance to that point. Same thing if I pick a point over in a different quadrant. If I go along the x-axis and then up in the y direction, connect the radius, that sets me up for another point. I could do the same thing below the x-axis, and I could go down along the y-axis and then over in the x direction, draw my radius. I could go however would create a right triangle and be set up to work with this. So the one thing we know, every radius or radii in this circle is going to be equal to 4. So every time we drew that radius, it actually had a measurement of 4. The things changing were the dimensions of the legs of the right triangle. So the hypotenuse was always 4, but the legs changed a little bit. I know the Pythagorean theorem is a squared plus b squared is equal to c squared. Since the hypotenuse is the radius, which is represented by c in the equation, we'll be squaring 4. We just have to figure out what a and b are. Well, for each of those 3 triangles I've drawn, a and b would be different numbers, but in an xy equation on the coordinate plane, we want to set it up so we can change and plug in those different numbers. So, if you think about it, one side of the triangle was really always represented by what the value of x was. In this first triangle here, I went over about 3 units in the x direction, so x was 3. In the second triangle, I went back -3 units. So those are just approximations, but that's whatever value I went in the x direction. Even below where I didn't go along the x-axis, I still have a leg that's equal to however many units I went in the x direction. So that can be a is just x squared. The same thing holds true for y. As I went in the y direction, here I went about 2 units. Here it looks like a little more. In this one I went straight down the y-axis and it looks like I was about 3 units. Those are all changing y values, but really what we're seeing is that y is always going to represent one of the legs of the triangle as well. So in this simplest equation, to create that circle, x squared plus y squared is equal to 4 squared. That's a simple equation. I can plug in values for x or y, and I can solve for what the missing variable is. So for example, if I keep going, well, 4 squared is 16, so now I'm set up. I have the legs of each triangle. or the x and y values squared, are equal to the radius squared. And I actually did that math. So going on to the next page, if I want to work with that equation, and let's say I just have the equation, I don't have the circle, I would plot this in a similar way to other graphs we've made where I could think about tabling it. So let's see what happens when I plug in 1 for x. All right, so I have 1 squared plus y squared is equal to 16. Well, 1 squared is simple. It's just 1. When I rearrange, I see that y squared is equal to 15. And then y is going to be equal to the square root of 15. Now, since we created that square root using inverse operations, it actually is the positive or negative square root. And that makes sense if you look back at the circle, because we have a y value that would be positive when x is 1, right about here. But then we also have a matching y value that would be negative when x is 1, right about there. So it makes sense that we get a couple. If I want to write this as a coordinate pair, I could say, okay, 1, and then the positive square root of 15, and also 1 and the negative square root of 15. I could do that for any set of x and y values I wanted just by plugging in one of them to solve and see what the other one is, and I could generate lots of coordinates for all the points on that circle. So this is kind of a simplest equation we could have for a circle. Had the radius been 5 instead of 4, the only thing that would change would be the hypotenuse of the triangles we were working with. So it would be x squared plus y squared. Let's say the radius was 10. So our new equation would be x squared plus y squared is equal to 100. We'll always square that radius. So that's another different circle. It would still have a center at the origin, but the radius would be 10 instead of 4 in that first example. So those are the simplest types of circles we'll be working with. Where circles get a little bit more challenging, let's go to a whole fresh new page. They'll get a little more challenging if that circle's not centered at the origin anymore. So if I draw, well, let's draw the circle first. If I draw a new circle, we're working, guys. We'll try freehanding the rest. Forgive me for my non-perfect circle, but it'll help us see the points we're trying to make here to keep the video moving. So, if I move this circle, like this, and let's say we center it over at, we'll just go approximately, let's call that 9 for the x direction, and then 1, 2, 3, 4, 5, 6 for the y direction. So the center of this circle is at 9, 6. I'll actually write that out here so we have room inside the circle. So we've got this new circle. Our radius, let's call it 4 still. So I know I'm not perfectly to scale, but we'll write those in and make our own scale here. So my radius is 4 units. This circle still follows the same rules of all circles, which means that all the points on it will be equidistant from that center. The difference comes in the Pythagorean theorem that we'll be using, because all of a sudden, well, we can represent our radius the same way as before. Oh, that's not a good one to draw. However, what changes will be how we represent the legs of the triangle. So I've drawn a couple right triangles like before. They have a radius of 4 units, which is also their hypotenuse. We can't just call their legs x and y, though, because this looks about 3 units, but the x value of that is no longer 3, we're moved over from the origin, so we're actually over like 12 total units on that. So that kind of changes things when we think about where the center is, and we have to account for that somehow. So we can similarly think about the Pythagorean theorem, but we don't just use x and y in it. To represent the leg that is moving along the x direction for this circle, or for this triangle that gives you a point on the circle, we'll still use x because we want to be able to plug in different values for x. So here, let's look at this one. So right now, this point that's actually on the circle is over here at approximately 12. However, I said the center was at 9. So the length of that side of the circle moving in the x direction is really only 3, and I think most of you can get to that just thinking about it, because the center's at 9, we're getting over to an x value of 12, so we've moved 3 units. To find that length, we take the x value of the point on the circle and we subtract the x coordinate of the center. So we're taking away 9, in this case when x was 12. Similarly, if we were over here, let's say at this point where x appears to be, let's call it 5, then to get the length of that side, you would have to look at, okay, we're centered at 9, this x coordinate's at 5, really the difference there ends up being -4. We're going to be squaring, so it won't matter, that absolute value is 4. That's the length of the x directional side of that right triangle. So those x values minus the value of the center give us the true length of a side of that triangle. The same is true in the y direction. We'll take whatever the y value is of a coordinate on the circle, and we'll subtract the center to get the true distance of a side of that triangle. So in this case, let's say if I called x 12, unfortunately I haven't done the math ahead, let's see here. So having an x value of 12 would give us 3, 3 squared is 9. So this would be, let's call a y value the square root of 5. Well, unfortunately, guys, my numbers aren't quite working out perfectly, but just hypothetically speaking, let's add up and say we have a y value of 10, because that's what it looks like. I know those don't multiply to 4 squared when we square them in the Pythagorean theorem, but the idea would still hold that the length of this y-directional side could be found by taking the 10 that's part of the coordinate and subtracting 6 to call that 4 units. So we can still work the same way to get the lengths of those two sides of the right triangle. I'm going to erase my numbers because they weren't correctly written or thought out to give us a good example, but we're going to find some values for ourselves. So now we have an equation with a radius of 4 units, and I can tell the center is at 9 and 6 for the x and y values because those are what's being subtracted from x and y. So right away, I know the center, I know the radius. Even if the equation was written like this, which it often will be, I still know the radius because it's always going to be the square root. This is the radius squared that I just circled. Alright, so if I want to go through and find points on the circle, I can try plugging in some different values to see what I get. So let's look at when x is 10. So 10 minus 9 squared plus y minus 6 squared is equal to 16. If I do that math, well, 10 minus 9 is just 1, and squaring that stays 1. So I have 1 plus y minus 6 squared, and that ends up being equal to 16. I'll roll to the next page so we have plenty of room. So 1 plus y minus 6 squared is equal to 16. At this point, we have a couple different options for how we proceed in solving this, since we're kind of given a perfect square. I think the easiest way would be to rely a little bit on a calculator by subtracting 1 to get y minus 6 squared is equal to 15. And then at this point, using inverse operations, taking the square root like we did in the last example, and we'll see that y minus 6 is equal to the positive or negative square root of 15. The reason I referenced using a calculator here is because as we continue, I'll see that y is equal to the positive square root of 15 plus 6, and y is also equal to the negative square root of 15 plus 6. Those are fine answers. They're actually really excellent because they're in exact form. But for me trying to visualize a point on the coordinate plane, I have a little trouble discerning where the square root of 15 plus 6 is at. So this one, it might actually be best to approximate by using a calculator to get the square root of 15. So if we do that, we'll take the square root of 15. We'll see that it's approximately 3.87. And then we can write that into our equation. So that's 3.87 plus 6 and negative 3.87 plus 6. And then from there you could simplify and get your coordinates. So we plugged in 10 for x. When we combine these, we'll get 9.87 for one coordinate. So when x is 10, y is 9.87. And then when we do negative 3.87 plus 6, we end up getting 2.13. So those are our two coordinates. This time it makes sense that both our y values are positive, because if you look where the circle's positioned, you won't have negative y values ever. So that's not an issue that it didn't look exactly like the last one. But there you have two good examples working through circles. You can always identify the center of the circle by looking at what is added or subtracted inside the parentheses with x and y. And you can always identify the radius as the square root, or what's being squared, on the other side of the equation. So there's a great connection with the Pythagorean theorem to the equations of circles. Please use this idea to do those 4 problems on today's worksheet. If you have any questions, let me know during office hours, and good luck, guys.